Right, so that stiffness of the spring, 800 newtons per meter. And what else is probably going to be relevant that's given to us in the text or elsewhere? Yeah.
The 200 millimeters unstretched length and 500 millimeters stretch.
Right, so good. You picked up on both of those pieces. The diagram tells us that distance between A and B, the equilibrium length of that spring. But keep in mind when we make the free body diagram, and we can always come back to this step once we discover this if there's a problem later, the free body diagram won't reflect that 500 millimeters in this case because we only are putting forces down, so it might not appear there. So what's the symbol we use for the unstretched length of a spring? The delta was the deformation or the change in length of the spring. So it can change depending on where you're looking, but based on the slides I presented, what meant unstretched length of spring? Just so that way if you look at the Hooke's law, it works. So I used L naught to be the unstretched length of the spring. So if it's just on the table, not attached to anything, then the distance from end to end of the spring, I'm going to convert it to base units right away here, so 0.2 meters. All right, the other point that we would want to put in the given is the current length or the equilibrium length of the spring. So what was the notation for the stretch length of the spring? Right, L prime is what I used, so just so it's coherent with the notes if you go back, the current length or the stretch length of the spring, it's now 0.5 meters when it's attached to A and B and this thing is in equilibrium. So both of those we do want to include in the given. And what are we trying to find here? Right, so we want the tension in those two cables. Just so it matches my notes, I will name them TAC, TAD. I know they're cables, so they can only hold tension. Oh, you're right, BC and BD, yeah. B is the center in this one. Right, so this will match, when I get to the free body diagram portion, I will use these. You can name them whatever you want as long as it makes sense with the picture that you draw. All right, so that's all we need to find. Now we have our free body diagram. So first step of the free body diagram is we want to do what? Right, what's the point of interest we want in this problem? Right, so B, again, for particles, it's usually pretty apparent. But B will touch the tension in BC and BD. For example, we selected A. It doesn't touch BC or BD, so we're not going to be able to see the force in BC or BD. So B is our best choice here. We are not given a coordinate system, so we may establish one. So I will choose X right, Y up. We have a coordinate system. We have our particle or object of interest. So what do we need next?
Forces.
Right, so what forces will act on B?
Tension of BD.
Right, so the tension in BD. Right, so right away, right, you have the dimensions there. So with the naming convention I've already used here, we can represent this, we can dimension this with 3, 4, 5. Or if you like to use angles, that's about a 37-degree angle if you want to use that. All right, so force and dimension done for BD. Yeah.
BC.
Right. So,
that's a 1, 1 square root 2 triangle.
Right. So if you like ratio triangles, 1, 1 root 2, or 45 degrees, if you prefer that. Yep.
If we just had 45 degrees there and like tension BC, that'd be all right.
Yeah. So either one, I'll put both here just for the example, but one or the other, it gets a little cluttered with both, but that's fine. Or again, the other alternate would to be put point C up here and give its coordinates would also be perfectly fine. So any or all of those, as long as I know when you get to the equation step, how are you finding how much of BC is in X, how much is in Y? What else is affecting point B? Right, the force in the spring. Now remember when I talked about springs, I am going to, no matter what in my drawing, assume the spring is in tension. So it's going to be pulling on point B. And I'm assuming this because the way that I gave you Hooke's law also makes that same assumption that positive will mean tension, negative is in compression. We actually know already that the spring is in tension, but even if we didn't know this, we'll still make that assumption. It could turn out to be the opposite, and that's okay. And even if I knew it was in compression, actually, I would still draw it in tension down here. So what's the value of this? Do we know at this very moment what the value is? Do I have it written what the value is? Right, I don't. So we don't know it at the moment. We'll figure it out in the equation step. So I don't know it, so I'll just give it a variable name. I like to call it F sub k because it reminds me this force comes from a spring, but the picture doesn't care. B doesn't care if it's being pulled on by a spring or by a rope or by a hand. It just knows a force is a force. So Fk, that will remind us later. So this is the complete free body diagram labeled and dimensioned forces, our point of interest, and a full coordinate system. Any questions on any part of this free body diagram?
Say we wanted to put the points up, like the 400 and 400 there, given like maybe a different situation. Would it be okay to convert it right to meters?
Right, yeah, I would say probably you're better off always converting like I did here to your base units.
I would rather.
Right, so I would include that. So if you wrote 0.4 meters, same thing. Anything else on the free body diagram? Again, one of the most important aspects of this class is being able to make a correct free body diagram. That is why it's basically a deal breaker on a quiz or an exam not to have one. All right, so moving on, we're done with the free body diagram step. We have our equation step. In this case, we either assessed or were told that we're in equilibrium, so we may write that sum of forces x is 0, and we may write that sum of forces y will be 0. That's true because we're in equilibrium. So equation 1, what's the right-hand side here going to contain? Anyone? All right, negative Fk. This needs to be kind of immediate recognition here. Yeah.
TBC cosine 45.
Right, so TBC cosine 45, or you can use 1 over root 2 TBC. Same thing. This is component is pointing to the right, so it's positive. And what else is here?
4/5 TBD.
Right, 4/5 TBD. Also, that component points to the right, so in the positive x-axis. So these two are positive, that's negative. One equation, 3 unknowns at this point. So we're going to set it aside and wait for more equations to come in. Equation 2, sum of forces y. What do we have here?
TBD sine 45.
Right, so sine of 45, which is 1 over root 2 TBC. And that component is up in the positive y direction. And what else do we have here? The vertical component of BD is down, which is defined as the negative y direction, and 3/5 of it points just down. So 2 equations, 3 unknowns, nothing at the moment is solvable. We're out of equilibrium equations. We're in 2 dimensions, so there is no z. So in this case, where are we getting another equation from? Right, we haven't used Hooke's law yet. So that's why, looking back here, Fk, that reminds us, oh yeah, there's at least one spring. We're going to need Hooke's law equations. So Hooke's law, the way that I presented, is that the force in the spring was the spring constant times the equilibrium length minus the original length. So again, in the order that I presented it, positive will mean tension and negative will mean compression. And if we look back at our givens, we are given or we quickly determined all of these values. So we can, from equation 3, determine that the force in the spring is 240 newtons. We can also see we now have 3 equations and 3 unknowns. Fk was an unknown over here. So Fk, TBC, TBD, 3 equations, 3 unknowns. So it was a solvable system at this point. So I kind of jumped ahead to the solve step, but that's okay. We can kind of go back and forth. Solvable system, we already have Fk. Now we can take this and put it back into equation 1 and equation 2. So what I would do is solve equation 2 for one of my unknowns here. So I could say that TBC is going to be 3 root 2 over 5 TBD. I can put that then into equation 1 along with the 240 newtons. So I won't go through all the details of this, but we get the tension in BD. You should get 171 newtons. And TBC is 145.